Hey there, and welcome to this explainer. So, today we're going to dive into something that's literally happening all around you, right this very second. It's totally invisible to the naked eye, but it's absolutely crucial to how our weather works. We're going to follow the story of just one single, invisible parcel of air and see how it acts like this ridiculously powerful sponge, just soaking up and holding the moisture of our entire world.
I mean, it's a pretty wild question when you really stop and think about it, right? Just look up at the sky. How does all that seemingly empty, completely transparent space around us manage to carry the massive, literally crushing weight of future storms, those towering clouds and thick fogs? Well, to crack this central mystery, we really need to zoom in and understand exactly what's going on inside that invisible pocket of air.
Okay, let's dive into this. The answer boils down to something called atmospheric humidity. Put simply, this is the actual physical weight of the water vapor packed inside our little parcel of air. Like, imagine drawing a box in the sky, right? A box that's exactly 1 cubic meter. Atmospheric humidity is just measuring the exact grams of water stuffed inside that specific box. So it's not just that sticky, gross feeling on a hot summer day, it is a very real, measurable physical weight.
And that physical weight brings us to what's basically the golden rule of meteorology. Think of our parcel of air like an invisible sponge. As the temperature of the air heats up, this invisible sponge essentially grows. It expands its capacity. The golden rule is, the higher the temperature, the more water vapor the air can hold. It's that simple. The temperature and the pressure of the air completely dictate its absolute maximal capacity for moisture.
So what exactly happens when this invisible sponge goes to work? Well, water is constantly evaporating into the air, right? From oceans, lakes, the ground, you name it. But obviously this can't just go on forever. Eventually, depending on its current temperature and pressure, our air parcel is going to hit a wall, a hard limit. It literally cannot accept a single drop more of water vapor. And when it hits that absolute maximum capacity, that's when we say the air is completely saturated. The sponge is maxed out, totally full.
Now, we hear the term relative humidity on the weather report practically every day. But it's not some scary, complex math. It's just a simple ratio. It's the amount of water vapor our air parcel actually has in it, divided by the absolute maximum amount it could hold if it were fully saturated at that exact same temperature. Multiply that by 100, boom, you've got your percentage. It's really just telling us how full our invisible sponge is relative to its limit.
Okay, so let's put our air parcel into motion. Imagine a gust of wind comes along and pushes it right up the side of a mountain. What do you think happens to our invisible sponge when it starts rising high into the sky, where the whole environment is changing? Just take a second. Try to guess what happens to its relative humidity as that altitude increases.
So here's the cause and effect breakdown of that journey. As the altitude goes up, the temperature of the surrounding environment goes down, right? So our parcel starts to cool off. And remember our golden rule from earlier? Colder air holds less moisture. That means the absolute maximum capacity of our invisible sponge is actually shrinking. Now, the actual physical amount of water inside hasn't changed at all, but because the sponge itself is getting smaller, it's suddenly way closer to being full. So as it rises and cools, its relative humidity shoots right up.
Actually, this is a really good time to quickly contrast relative humidity with absolute humidity. While relative humidity is all about that percentage of capacity, absolute humidity is just the sheer physical weight of the water vapor in a unit volume of air, usually measured in grams per cubic meter. Absolute humidity doesn't care at all about temperature or capacity. It's literally just the raw weight. And to measure that raw, physical weight, meteorologists use some pretty cool specialized tools, specifically the hygrometer and the psychrometer.
So to really get a read on our air parcel's vital signs, we look at two very specific temperature readings. First, you've got the dry bulb temperature, which is honestly just your standard, actual ambient air temperature. Nothing fancy. But the wet bulb temperature, that reveals something a bit deeper. It represents the absolute lowest temperature the air can be cooled down to purely by the evaporation of water. You can kind of think of it as a measure of how much cooling potential the air still has left in the tank.
Here's how it works in practice. If our air parcel is really dry, water is going to rapidly evaporate from that wet bulb, which drops its temperature significantly thanks to the power of latent heat. Basically, the evaporation is pulling the heat away. So a huge difference between the dry bulb and wet bulb temperatures tells us the atmosphere is super dry. But if the air is already completely stuffed full of water, if it's fully saturated, no evaporation can happen at all. In that scenario, both thermometers are going to read the exact same temperature.
Which brings us to an absolutely critical threshold for our invisible sponge, the dew point temperature. This is the exact temperature our air parcel has to be cooled down to for saturation to happen at a constant pressure. And the dew point is so fascinating because it's essentially a fixed marker. It will only ever change if the actual physical amount of water vapor in the air changes. Otherwise, it stays perfectly put.
All right, let's jump back to our air parcel's journey upward into the sky. As our parcel climbs higher, the dew point actually doesn't stay perfectly static. It does drop, but very, very slowly. It follows a lapse rate of about half a degree Celsius for every 1,000 feet of altitude it gains. And this slow, steady decline sets up this almost thrilling kind of race as the air pushes up into the colder and colder atmosphere.
And this brilliantly illustrates exactly what happens. If we track the ascent from mean sea level down at the surface, the outside air temperature might be 20 degrees Celsius, with the dew point sitting at 16 degrees. But as our parcel gets forced upward, the outside air cools rapidly, while the dew point is cooling much, much slower. By 1,000 feet, the gap is closing. At 2,000 feet, they are practically touching. And right around 3,000 feet, they finally converge.
So the crucial takeaway is right here at this exact moment of convergence. When the dry bulb temperature, meaning the actual outside air temperature, cools down so much that it perfectly matches the dew point, well, our invisible sponge has officially shrunk to its absolute limit. The relative humidity instantly hits 100%. It cannot hold another drop.
And honestly, this gives us one of the most magical meteorological principles of all time. With just a tiny bit of further cooling and a little air movement at this 100% saturation point, the invisible suddenly becomes visible. The base of a cloud forms exactly where the dry bulb temperature meets the dew point. Boom! Our invisible air parcel has officially given birth to a cloud.
Now, as this cloud forms, some pretty fascinating physics step in to govern how it behaves. First, we see that the spread between the free air temperature and the dew point is at its absolute least. It's zero, because the air is now fully saturated. We also find that the saturation pressure over water is actually higher than it is over ice inside these newly formed clouds. On top of that, if this air gets lifted adiabatically, which just means it rises without transferring any heat to its surroundings, its humidity mixing ratio stays entirely locked in, completely constant.
Okay, so now that our cloud is born, what actually dictates its ultimate fate? Is it going to rocket up into a massive thunderstorm, or just settle into a nice, gentle fog? Well, that all comes down to atmospheric stability. In physics, stability is basically defined as the ability of an object to come right back to its original position after any outside force is exerted on it.
It's kind of like a giant puzzle. Imagine our air parcel acting like a ball sitting at the bottom of a bowl. If you push it up the side, it naturally sinks right back down to where it started, right? That is positive stability. Now picture that same ball perfectly balanced on the very top of a steep hill. Even a tiny little push makes it accelerate wildly away down the slope. That is negative stability, and that's exactly what leads to those huge, towering storms. Finally, if the ball is just sitting on a completely flat table and you push it, it just stays wherever it ends up without accelerating. That's neutral stability.
The whole journey of our invisible air parcel, from the ground all the way up to the sky, is just a masterpiece of temperature, pressure, and capacity. It's this incredible continuous cycle happening right above our heads every single day. So the next time you look up and see a cloud drifting by, I want you to ask yourself just how much invisible water was pushed to its absolute limit, cooling degree by degree until that invisible sponge could hold no more, all just to paint that specific picture in the sky. It's pretty amazing to think about. Thanks so much for joining me on this explainer, and keep looking up.